This video is going to look at the magnetism section of the NotesQuest. You're going to see what is magnetism and basically come up with a general definition. Then we're going to see what ferromagnetic means because that's related to it. We're going to look at hard and soft magnetic materials and how we can make a soft magnetic material magnetized and also demagnetize it. So make something magnetic and not magnetic. We're going to look at field lines for different shapes. And also while we're at it, we're also going to look at electromagnets, which are a special type of magnet that can be switched on and off. Let's start by looking at what magnetism is. Well, certain materials just exhibit it. You don't need to know really why they do, but take a material, in this case it's going to be iron, and it's a magnetic material. Now what does that mean? Well, that means it's going to create this sort of invisible field around it. You won't be able to see it, you won't be able to taste it, you won't be able to smell it, but it's there. And how do we know it's there? Well, if you put another magnetic material, so it could be a little magnet again, or iron, a lump of iron, or some iron filings, it's going to experience a force. So that's how we know we're in the field, and that's what magnetism is. It's an area around a magnetic material where another magnetic material will experience a force. So an area around a magnetic material where another magnetic material will experience a force. Bit of a weird definition, but it's a weird thing. You also need to know some examples of ferromagnetic materials. So when we said a magnetic material here, what we meant was actually a ferromagnetic material. Ferro is from the Latin for iron. So that gives you your first one. The examples that are commonly learnt are nickel, cobalt, and iron. It's quite nice because you get them to spell out Nick, and iron is by far the most common. That's what you have in your blood. That's why your blood is slightly magnetic, but you need a very strong magnet to see that. So remember, it's Nick, it's the first letter of each of these, N-I-C. If we go back now, the next thing we need to look at is hard and soft magnetic materials. So there's two types. Hard magnetic, they are also called permanent magnets. These are ones that are hard to demagnetize and magnetize. That means they keep their magnetism, and sometimes that's really useful, like the magnets we have at school. So we often make those out of steel, which is an example of a hard magnetic material, and it will keep its magnetism. Once you've magnetized it, it's very hard to demagnetize it. So it's a hard magnetic material. A soft magnetic material, these are sometimes called temporary magnets. And these are ones that can be easily magnetized, that means made magnetic, and demagnetized. A good example of this is iron. It's very easy to magnetize and demagnetize. So this covers the two key types. Sometimes this is very useful. Sometimes you want something that will become magnetic and then lose its magnetism later on, and we'll see that when we look at electromagnets. Let's look at the law of magnetism now to see how magnets behave. Now, just like when we looked at charge, we said there was two types, positive and negative. There are two poles, we call them, for magnets. So let's take a bit of iron here. We call the two poles north and south. Now, as you probably remember or know already, the law of magnetism tells you that if we have two poles which are the same, north and the north together, they are going to repel. So same poles, that means we're going to get a repulsion, they're going to repel and move apart, there's going to be a force apart. However, the opposite case, where we have two poles which are opposite, we're going to get an attraction between the two. So the law of magnetism tells us that the same poles repel and opposite attract. And that's very useful to know. So, for example, north, north repel, south, south also repel, which I can represent with these arrows going apart, whereas opposites attract. So opposite poles, north, south, attract. You can never have just a monopole. If I cut this magnet in half, you're not going to be, aha, I've just got a north pole now. No, well, this side becomes a south pole, and then that side becomes a north pole, just like that. So you can't just cut a magnet and expect to get one pole. They always exist in pairs. And coming off the back of that, we need to know what the shape of a magnetic field is around one of these bar magnets. They always have a north and a south pole, sometimes colour coordinated like that. And we know that there's going to be a field around this, and humans need to represent that some way. So we do that using something called a field line. These are continuous. That means they don't stop. And they show us the direction and the shape of the field. For a bar magnet, it looks something like this. These actually continue all the way around and eventually come back around here. Because remember, they are continuous. That means we can't start them. The direction is from north to south. So it comes out the North Pole, and we have to draw arrows on to show that, and goes into the South Pole. You've just got to learn that. We've defined that as humans to be north to south. There's more like this. One other thing they don't do, they never cross. Okay, so you need to keep it nice and neat. We do not want to see this. We've just crossed, no good. Equally, we do not want to see it starting and then a bit of a gap and then maybe stopping there. There's two gaps here. They are not like this. They are continuous. We can never have it doing anything like that. So these are field lines, and you need to know some shapes for magnets when they attract, when they repel, and do other things. So over here, you can see the bar magnet over here. Again, you need to know that. Look at this field lines going from north to south. Remember, these actually continue around, but you can't draw them all. A horseshoe magnet is just a different shaped magnet, but you can again see the same sort of shape going from north to south. And the ones that we're interested in at this stage are at the bottom here. So when, unlike poles attract, you get a field that looks something like this. Okay, the field lines go from the north to the south pole, almost like it's reaching out to that and pulling it in. That's not what's happening, but it's a nice way of thinking about it. If those magnets were a bit bigger, the lines would actually become a bit straighter, like this, and we call that a uniform field. We'll see in year 10, 11 why that's really useful. That's a uniform or constant field. When they're repelling, which is shown here, there's a typo in the original image, you can see that the field lines aren't reaching out to each other, they're pushing up against each other almost like that. That's kind of where that repulsion comes from. You can think of it, remember they don't want to cross, so if you push them together they can't cross each other. Not quite what's happening, but it's a good way of remembering that field. The rest of it is like your usual bar magnet. If we go back to our mind map now, you'll see that we've now covered what it is, ferromagnetism, hard and soft. We're going to look at how you can magnetize things in a minute, and we started looking at field lines. So we're going to look at some different shaped field lines now that you've just got to learn at this stage. You can see them here. The first one is when we have electricity flowing in a wire. Now, for some weird reason, well, it's not a weird reason, but it's just the way our universe was made, when current flows in a wire, we get a magnetic field around that wire. Its shape is circular, and you can see that up here. The way you can tell the direction is by using your right hand and doing the grip rule. We'll go over this in class, but the thumb is for the direction of the current. So if the electricity is flowing this way, as shown by this arrow, and the thumb points upwards. This is your right hand, remember. This is called the right hand grip rule, because once you've done that, the fingers show the direction of the magnetic field. So you can see they're curling around like that, so we know that direction is in that direction. As we go further from the wire, these field lines get further apart, showing us that it's weaker. That's one really useful thing with field lines that we didn't mention earlier, but it is important to know. The closer together the lines, the stronger the field. Okay, so you might add that to your notes. A stronger field when the lines are close together. And that's why they're useful, because we can tell where the field is strongest. If we have a single coil of wire, you can see we get this sort of shape shown over here. And this is with the current flowing around like the loop, and you get this sort of, almost like a bar magnet, but on a smaller scale shape there. A solenoid is the next one, and this is just a coil of wire. So if you just get a wire, wrap around your finger, turn it into a coil, and you get a very similar, you'll see the similarities between the two, between the bar magnet and the solenoid. The only difference with the solenoid I'm going to just sketch one here, coil of wire going around like that. This is connected up to a battery. We've got current flowing that way round. Remember, it goes from positive to negative. The only difference is we actually get a field in here that we can sometimes use for things, and it's a very uniform field. So the lines are equally spaced and parallel. That tells us that it's uniform. And then around the outside, it just looks like a bar magnet. So it's quite nice and easy to remember. It kind of goes out like that. We'll look at why those are useful later on. Let's just go back to our other shapes. The other one you need to know is the Earth. And the Earth acts almost like it's got a bar magnet in its core, like that. Now, actually, slightly confusingly, this is an interesting little fact. Here's the Earth. This is what we call the North Pole. Well, actually, it's not a North Pole. If we had a magnet in the middle, it would actually be such that this was a South Pole here and a North Pole here. Why? Well, because if you think your compass, the North Pole of your compass points towards the North Pole of Earth. But remember, it wouldn't point there unless that is a South Pole, because opposites attract. So this is a North Pole here, and this is South Pole here. You can see the North pointing that way towards the South Pole, and that's because it's actually a South Pole. We call it the North Pole because the North Pole of compasses point there, but actually if we can dig into the Earth, and imagine there's a big magnet in there, it would actually be a South Pole just underneath the North Pole's surface. So a bit confusing, that, but interesting fact. Now, why are solenoids useful? So these coils of wire. Well, we can make something called an electromagnet, okay, which is up here. What we do is we get a coil of wire, connect it to some sort of power source, a battery. Often it's good to have a switch in here, so we can switch the current on and off. And if we put in the middle an iron core, so we could just use a nail, that's what we'll do in class. We call that the iron core because it's in the center of the core of the wire. This coil here, remember, is the solenoid. Now, what happens when we switch this on? So we close this switch. Well, when we close the switch, current flows, and that creates a magnetic field around the solenoid. So there's a magnetic field around the solenoid. Now, we've got the iron in there. Remember, iron is a soft magnetic material, so it's going to become magnetized. That means it's going to become magnetic. So that makes this magnetic. There'll be a north and a south pole somewhere. And that's very useful because now we could attract other magnetic materials, maybe some paper clips, or if we're in an industry, we might pick up some cars with this, make it much bigger so we can move cars around. When we reopen the switch, so now we open it up, so we're back to this, the current stops flowing, and the reverse happens now. Magnetic field, so we get the magnetic field is no longer there, goes to 0. So the iron core demagnetizes. That means it's no longer magnetic and we can drop the things off. So an electromagnet is really useful because advantages, and the big one is that it can be switched on and off. And you can think of many times when that would be useful. Just take your recycling. If you want to separate your iron cans from your aluminium cans, aluminium is not magnetic. So if we get a big electromagnet come over these here with this electromagnet, it's going to attract the iron up, which is going to stick to the surface, and then we can go drop it off for recycling. So that's one of the big uses of an electromagnet, and they are used in lots of places. If we go back now to here, we've now looked at electromagnets and we've looked at field lines in the different shapes. We just need to look at how we can actually magnetize some iron. We've looked at one way. Over here, we said we can magnetize this iron core by putting it in a direct current. But let's look at the ways that we can magnetize. So to magnetize some iron or any other soft magnetic material that we mentioned earlier, the options are. And before we do this, it's a good idea just to understand how things become magnetized and demagnetized. Now, when we're looking at a lump of iron, you can imagine it as being split into a load of little sections called domains. You might sometimes hear this as domain theory. Imagine these as tiny little magnets. So I'm drawing these magnets pointing in random directions like this. The top of the arrow we can imagine as north and the bottom of the arrow as south. Now at the moment these all have small magnetic fields around them, but they cancel out. So over the millions and millions of domains like that one and that one would cancel out to give you 0. that one and that one would also cancel out. So overall, the whole iron, this is not magnetic. So to magnetize it, we need to get all those domains to line up. So if we get something like this, and there might be a couple of ones just change their mind and going a random way, but can you see overall, we can see that most of them are pointing the same direction, making this side north, this side south, so we've got a magnetic field going around like that. So we need to line those domains up if we want to make something magnetic. So how do we magnetize some iron? Well, one way is to use the single touch method. What does that involve? Well, that involves you getting some iron like this, getting a magnet like this, and going along the surface like this, back into the air and back round. What this does is, well, this magnet here is going to attract all the south sides of the domains to line up such that they're like this. And that's caused it to magnetize because they're attracted, these little domains are attracted to this here. If we went back and forth like this, well, you just jumble them up and it wouldn't work. The other method is the double touch method, and the clue's in the name. So we'll start off with our lump of iron that we want to magnetize. Here it is, and at the moment the domains are pointing in random directions. Now we're going to start off by using one magnet here, with its south pole here and its north pole at the top. We're going to move that one round like this. Okay, so it's moving up and around like that. But on the other side, we're going to do the same, but move in the opposite direction. But this one with the north pole facing downwards. So what does this mean? Well, remember we had these little domains. One side was north, one side was south. If you think about what's going to happen in this on this side of the magnet, what is going to happen? Well, the north pole here is going to attract the south pole of these, and it's going to face them all like this. This one here, the south pole is going to attract the north pole, so that's also going to make all the domains line up like this. So you can see they're all lining up in the same way, and now we have a north pole here and a south pole here, so we've magnetized it. The final method involves a solenoid, and as we saw earlier, if we just get the solenoid and put some current through it, that's going to create a magnetic field. If we then put our lump of iron that we want to magnetize in, the magnetic field of the solenoid is going to cause all the domains to line up. So all those domains are going to start facing the same way. I'm not sure which way it is in this case, but let's say it's that way. You could work it out if you want to, but you don't need to do that in year 9. So that's one way of doing it, but you need to use a direct current. So you have to have the current flowing in one direction. So you need to use a battery. You can't use the mains electricity for this. But what happens now if you want to demagnetize it? So how could we demagnetize some iron? Well, we need to jumble up those domains. So a nice easy way is just to hit the iron hard. So you can hit it on the table, hit it against a hammer. That's going to jumble up those domains. Another option, you could heat it up. If you heat it up, that's going to give those domains some energy. They're going to start jumbling up. Remember, we want to go from this, they're all pointing the same direction, to this. So we need to put some energy in to jumble up those domains. So hopefully that's been useful. Why would we want to magnetize something? Well, sometimes we want to turn steel into a magnetic material, and this is the options we could use to do that. And once steel's magnetized, it keeps its magnetism for a while. The only other thing, just briefly to touch on, is with these, sometimes you want to make these stronger, these electromagnets. How can we get that to pick up, say, more stuff? Maybe we want to pick up a car this time. Well, one way, we could increase the voltage or the current. If you increase that, so we could go from 10 volts to 20 volts, that would cause more current to flow. That's going to create a stronger magnetic field. We could also increase the number of turns on here. What does that mean? Well, that just means wrap the core around more times. And we'll do this in class with an experiment. Those are the two most, the best options here. We could also make the iron core bigger, or we could, if there wasn't an iron core, we could put one in, because that's going to make it better, as we discussed earlier. So going back to our original mind chart, hopefully now we can see that we've covered everything. How can we magnetize something that's now been covered? And we also looked a bit at how we could demagnetize it. Thanks for watching.